All right, hey everybody, welcome to the first video of the first unit, where we're going to be talking about the real number system. And to get us started at the beginning of this unit, we're going to be focusing here on part A, where we're just going to be classifying our real numbers. So the first I can statement for today is going to be I can classify real numbers into subsets. So make sure you've got your packets out and you're going to just begin taking notes with me here. You're going to follow along in the video. So what we've got here first is that we can group real numbers into different categories or subsets. Just like we can organize fresh produce at the grocery store into fruits and vegetables, we can label numbers as either rational or irrational. So all the numbers that we have in the world, we can break down into different categories or subsets. And the first thing we're going to do when we take a look at those numbers is we're going to break them up into either rational or irrational. All right. So to get started, we're going to focus first on just rational numbers. So rational numbers are numbers that can be written as a fraction. And what we mean by that is that the decimal either stops, it terminates, or the decimal could go on forever and ever with a repeating pattern. So these are the things that would describe and define a rational number, and I'm going to give you guys some examples over here. So a rational number is first and foremost something that can be written as a fraction. So for example, the number 4/5, that is rational because it is a fraction. As a decimal, this decimal would stop, it terminates, it is simply a 0.8, just 8/10. So that's what I mean by it can be written as a fraction. And if it can be written as a fraction, it must be a decimal that stops, or it must be a decimal that goes on forever and ever with a repeating pattern, kind of like if you were to see a 1/3. You guys know that 1/3 is a 0.3 repeating. And so the 0.3 goes on forever and ever and ever. And instead of writing the dot, 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 I don't want you to put the dot, dot, dot. I want you to put, sorry about that. I want you to put the 0.3 with a line over it, because the ability to put the line over the decimal that repeats and goes on forever and ever and ever, that's how you know that it has the repeating pattern, okay? So again, those are your examples of rational numbers. Now, if it can't be written as a fraction, that's how you know it's irrational, okay? So irrational numbers are numbers that cannot be written as a fraction. And we have some examples of what we mean by that. If you see pi, pi is a number that's definitely irrational. Sorry about the bell. All right, so pi is irrational. Non-perfect squares. So if I were to try to take the square root of the number 20, since 20 is not a perfect square, when I try to take the square root of it, it's going to go on forever and ever in the calculator. Now I could also straight up write a decimal that does go on forever with no repeating pattern. So an example of something like that would be like if I had, for example, 0.1389, and then I put a dot, dot, dot. There's no repeating pattern. Nothing repeats for me to be able to put a line up above it, so I'm going to call it irrational. So back to rational, if you see something like a 0.458, 458, dot, 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 you know that that's rational because you could write this as a 0.458 with the line up above it to tell you that the 4, the 5, and the 8 repeat. So that's what I mean by a repeating decimal. Now, what if down here you saw a 0.48, 448, 4448? So here you can kind of see a pattern, like you got 48, 448, 4448, but none of that repeats, meaning I can't put the line over just the 4 and the 8, because if I did put a line over just the 4 and the 8, it should go 48, 48, 48, 48. So that's what we mean by repeating versus no repeating pattern, okay? So we're going to practice that with the decimals, because I feel like with the decimals, that's usually right at the beginning of the unit where some students kind of struggle between rational and irrational. So just taking a look here, we've got these decimals, and we're going to try to look at which one does not belong, okay? So here I see a 3/6, a 3/6, a 3/6, a 3/6, and a dot, dot, dot. Here is 1, 2, 3, 4, 5, 6. We've got 0.853279347, and then a 0.121121112. So all of these go on forever. That's what that dot, dot, dot means. But one of these doesn't belong with the rest. And hopefully you guys would agree with me that this is the one that doesn't belong because it has a repeating pattern. So this one doesn't belong with all these other decimals. So why do we want to say that this number right here is rational? Because I can write it like this. It has a repeating pattern, so this one is rational, and then these other three would be considered irrational. Okay, those are going to be IR for irrational. All right, let's look at another example over here. So we've got four more decimals. We've got a 0.985340. We've got a 0.345230498. We've got a 0.56556556. And we have 0.8s all the way through. So if I am looking again for which one doesn't belong, I feel like I see that this one doesn't belong with the rest because it has, again, a repeating pattern. So anytime you can take a decimal and you can make it look like it stops with one of those lines up above it, you know you've got a rational number. And anytime it goes on forever and ever with a weird funky pattern or with a weird funky number and no repeating pattern, then you know that you've got, again, an irrational number. All right, now down here, which one doesn't belong? So we've got the square root of 3, the square root of 9, we've got the square root of 18, and the square root of 20. So only one of these doesn't belong with the rest, and it's this one, because it's a perfect square. So why is this number rational? Well, it is a perfect square. So perfect squares are rational, okay? And then anything that is not a perfect square is irrational. And that's what I had back up here. If it's a non-perfect square, it's irrational. And then now let's add up in here, let's add a common one, the square root of 25. Most everybody knows the square root of 25 is 5. So since we know the square root of 25, it is rational. So if you know it's a perfect square, it's rational, but if not, it's irrational. So now let's take a look at this last set. We've got a square root of 50, a square root of 121, a square root of 139, and a square root of 200. Which one of these doesn't belong? You might not remember, but it's this one. This is the perfect square of 11. If you do 11 times 11, you get 121. So this one is rational because, I'm just going to copy and paste, it's a perfect square. There we go. So if it's a perfect square, rational. If it is not a perfect square, it's going to be irrational. All right, cool. So that takes care of the first page. Let's flip over. So what I'm going to have you guys do first is all we're going to look at is a variety of numbers, and we're going to determine just if it's rational or irrational. So remember, if it's a fraction or if it's a decimal that stops or has a nice repeating pattern, we'll put it over here. If it's anything with pi, if it's not a perfect square, or it just goes on forever and ever with no repeating pattern, we're going to put it on this side. So we're just going to go left to right here. So the 0.75, since that's a decimal that stops, we're going to put it over here. Okay, so I got a 0.75. We've got that one. 2/3 is a fraction, so I know I can write it in rational. All right, we do know the square root of 36. The square root of 36 is 6, so I'm going to put that one in here. All right, so 0.333 with a dot, 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 because I can put the line up over it to kind of make it look like it stops, but the line I know it repeats. That's a rational number. Now pi is the first one we're going to put on this side. Pi is irrational. All right, so we got that one. Now 20, it is a number that's rational. I can prove it by making it a fraction. So 20 over 1. Or I can make it look like a decimal that stops, a 20.0. So no matter how you spin that, 20 is rational. All right, we got a negative 6.5, so that's a decimal that stops. So I'm going to put that over here. All right, we got this one and this one. Now 0, again, you can make it a fraction by simply putting it over 1. 0.452, that one stops, so we're going to put that in rational. All right, now we're at 11. 11, make it a fraction by putting it over 1. All right, we've got a 0.5092 dot, dot, dot. And I don't see any repeating patterns, so we're going to put that one on this side. The 0.5092 is going to go over here. Dot, dot, dot. All right, we got that one. -8, you can make it a fraction by putting it over 1. And the square root of 40, well, since 40 is not a perfect square, we're going to put that one on this side. So we've taken all of the numbers and now we've grouped them into one of either two categories, either rational or irrational. This is basically the same concept, y'all, of me giving you a bunch of produce items up here and asking you to categorize it as either a fruit or a vegetable, okay? All right. Now, once we know something is rational, we're going to focus on the blue side, okay? Because once we've said that it is rational, we can further subcategorize it if we don't see any decimals, okay? So what I mean by that, and you can go ahead and copy this down if you want to, we already got the 3 that were irrational. I'm already going to cross those out and put them on the irrational side, because once it's irrational, there's nothing else that we can do about it. Like, it's just going to stay irrational. But if it's rational and we don't see any decimals, we can actually call it an integer. So before I do anything with this box, I just wanted to remind you guys that a number line is going to show you what all the integers are. So like -4, for example, that's an integer. 1 is an integer. These are your integers. And if we take the number line and only go from 0 up, that's going to be our whole numbers. The whole numbers are 0 and up. And then the natural numbers are only 1 and up. And if you think about it, if you were to naturally start counting, you would naturally go 1, 2, 3, 4, 5, 6. So that's what I mean by natural numbers. So you don't see any decimals here, do you? Okay. So we have, from this first box up here, we have all of these numbers that were in blue that were rational. And anything that doesn't have a decimal, we're going to further subcategorize it as an integer. Okay. So if it was a decimal, I'm just going to leave it out here in rational. So we had a 0.75. 2/3 is a decimal. That thing goes on forever and ever and ever. That's a 0.666 repeating. We have a 0.3 repeating that we need to put in rational. That's a decimal. So I've got this decimal, that fraction slash decimal. We've got that one. This is a decimal that needs to stay just in rational. This is a decimal that needs to stay just in rational. So we have some space down here where we can put these decimals. And that takes care of everything that that had a decimal, all right? Now the ones without a decimal, we can call integers. So I can call the square root of 36 an integer. I can call 20 an integer. It's on the number line. 0 is on the number line. And 11 and -8 are also on my number line. So that's what I mean by taking anything that you called rational and being able to further subcategorize it if it's on the number line as an integer. Now I'm going to scroll down and I'm going to let you guys go ahead. The blue numbers, all I'm going to do is recopy the blue numbers, because if we said it was rational and left it out there, I'm going to leave it out there as rational. So these were the ones that couldn't be further subcategorized. I'm just kind of rewriting them now. These were the fractions and the decimals. So I got that one, that one, that one. I need this one and this one still. So -6.5 goes here. And the 0.452 went here. So we've got the rational numbers that stayed rational. Irrational is already over here. Like I said, once it was irrational, there was nothing else we could do. But now my goal is to take a look at these green numbers here and see if any of them can be further subcategorized as whole numbers. All right. So when I look at this list, anything that is a whole number can go into this box. So remember, whole numbers are 0 and up. So what I'm going to do now is I'm just going to look at this and I'm going to say, okay, I see a 0, I see an 11, and I see a 20. And then the other numbers, oh, and the square root of 36 can go in here, because that's a 6. So the only one that now has to just stay an integer is a -8. Because it's a negative number, it can't move into this box. So we've got the fractions and decimals are rational. And then here we have the -8 integer. And these numbers are also integers because you see how they're in that integer box still, but they're just in a smaller category for whole numbers. And if you guys flip over now, we finally have the entire real number system where we've got rational and irrational. This is, again, if you just flip over to the next page. And in rational, you can now see all of the subsets: integer, whole, and natural. So the natural numbers, remember, those were the counting numbers from 1 up. And in our list, when I look at integers, the only ones are going to be this one, and this one. So 11, 20, and the square root of 36 can be further subcategorized. I'm going to write them here so I don't forget. The 11, the 20, and the square root of 36. These are my natural counting numbers in the list. If I were to start counting and I naturally started at 1, I would eventually get to 11. Then I'd eventually get to 20. And of course, the square root of 36, like we said, that's a 6. So of course, 1, 2, 3, 4, 5, 6, I just got to it. Now out here, we needed to leave the 0. 0 was the only number that's right there that can't move into natural. And then we had the -8 was the only integer that couldn't be moved into these boxes. And then we had all those other decimals and fractions out here. So I am simply rewriting our list now. And all of the numbers will officially be in the correct spot, which is what today's I can statement is. I can classify numbers into the appropriate subset. So you can see here, I've got numbers that are rational and I've got numbers that are irrational. And then on this rational side, I was able to say that 8 is also an integer. 0 is a rational integer that is also whole. And then 11, 20, and 36, the square root of, are also rational, integer, whole, natural numbers. So we've got everything in the list now in the best spot in the real number system. It's a lot like saying out here, okay, so over here, maybe we're talking about the state of Virginia. And if you're in the state of Virginia, maybe here, this is like saying you're in Springfield. And then this might be like saying you're at Irving Middle School. And then this might be like saying you're in my math class right now. So if you're in my math class right now, you're definitely in Irving Middle, which means you're definitely in Springfield, which means you're in Virginia. And that's how those charts work. So let's practice now. We're just going to practice with the real number system, and we're going to practice together putting all these numbers that are over in this circle. We're going to put them in the right spot together now. I did want you guys to get some practice labeling the different subsets here. So go ahead and take your notes now with me. I'm going to type it, but you can label that this box is going to be the rational side, and then we're going to have the irrational side. And then you can further subcategorize rational numbers as either integers. So you got your integer box. Sometimes if the integers are 0 and up, we can call them whole numbers. And if the number is 1 and up, then it would go into this last spot, which is going to be your natural numbers. So we've got our subsets labeled, integer, whole, and natural. And the two big categories were, again, rational or irrational. This whole thing will make up something called the real number system, which is, again, this whole first unit. And now let's dive on in. We're not going to need to put the number in every single spot that it belongs. We're going to put it in the best spot, kind of like right here. By putting it in this spot, it's in the best place, and we know it's also considered all of these things. So let's just start with 0. So 0 is rational. It is on the number line, and it is a 0 and up number. So 0 is going to go right there for whole. I can't put it in natural because it's not 1 and up. All right, cool. So we've got 0. All right, let's do 3. So it's rational. It's on the number line. It is 0 and up. And if I were to start counting, I would eventually get to a 3. Cool. So we got 3. All right, let's do 4.5. So it's a fraction, which means it's rational. And because it's a fraction / decimal, like a 4.5, I can't move it into integer because remember the integer is only the number line. I do understand that like 4.5, I could say, hey, there's 4.5 on a number line, but I'm certainly not going to have it like labeled on a traditional number line. All right, so we've got 4.5 is right there, 4.5. All right, so 64/8. So if you're thinking that you're going to put it in rational, you're right, because hello, it's a fraction. But do the math, y'all. What is 64 divided by 8? Since 64 divided by 8 is 8, it can actually go all the way down here because when we're counting, we would eventually get to 8. So we can put our 64/8 right there. It's a natural number. All right, cool. So the square root of 16. Most of you know the square root of 16 is 4. So since it's a 4 and I would eventually count to a 4, I'm going to put the square root of 16 down here for natural. All right, so we got that one. All right, now we're doing 3 squared. Friendly reminder that that's not going to be a 6. This means to do 3 times 3. All right, so 3 times 3 is 9. I am running out of room, so I'm just going to kind of list them off to the side right here. There's my 3 squared. All right, now 8.22. Friendly reminder that my birthday is on August 22nd. Not sure if anybody remembered that, but that's where I see that decimal. But since it's a decimal that stops, we're going to put it up here at 822 under rational. All right, we have a 0.3 with the 2 3s with the line over it. So since it's repeating, that's a 1/3, which means it's going to be rational. 6.3 is a decimal that stops, so it's rational. Negative 4.5, so I'm a little bit running out of room, but I'm going to put a negative 4.5 up here. That's rational, and since it's a decimal, I can't put it into integer. All right, 6/8. That does reduce. This reduces to a 3/4, which would be a 0.75. So again, it's a fraction or a decimal that stops, 0.75, and I'm running out of room, so I'm just going to put that up here for rational. All right, we have a negative 12. So a negative 12, it is rational. And since it's on the number line, it's going to go into integer, but because it's a negative, it can't keep going down into whole or natural. All right, and then we have 9 pi. So 9 times pi. Anything to do with pi is going to be a number that goes on forever and ever and ever. Pi is a number that goes on forever and ever, and now I'm just making everything in it 9 times bigger, but it'll still go on forever and ever. So anything with pi is irrational. Friendly reminder that if I had something in here like the square root of 5, since 5 is not a perfect square, I would put that right here. And if you saw one of the things that had a dot, 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 and it did not have a line up over it or no repeating pattern, that's also another type of irrational number. At this point, this concludes the video for today. So thank you for watching.